Good evening everyone. I am Chanda Devnath, one of the PMRF fellows of ISAR Badhampur. So I am the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pran from IIT Guwahati. So in these classes I usually discuss about some previous year questions based on this topic, that is reagents in organic synthesis. So in the last few classes I have already discussed about some reagents like the oxidation, reduction, and some non-metal containing reagents, some metal containing reagents also. So in the continuation of the previous classes, so in the previous classes I was discussing about reagents containing transition metals. So till now I have discussed about titanium, ruthenium, palladium, copper, chromium, manganese, and zinc, iron, and cobalt. So till now I have already discussed this titanium, palladium, ruthenium, these four, and iron as well as copper. So all these are remaining till now. So today I will discuss about mainly this silver catalyst and rhodium catalyst. In the upcoming classes I will discuss about the others, and by next two classes we will be finished. I think we will be finished. So first we will discuss about rhodium containing reagents. So a popular method for the formation of substituted cyclopropane is the condensation of a dicarbonyl compound and an alkene in presence of metal catalyst, and the mostly common used metal catalyst is rhodium acetate. So if we use this type of diazo type of compound in presence of rhodium, it generates carbene. In presence of rhodium, it generates carbene. Through elimination of nitrogen gas. So elimination of nitrogen gas. So this carbene get inserted into this double bond, leading us this cyclopropane compound. This type of reagent can be also used for asymmetric cyclopropanation to synthesize some biologically important compound like antifungal, antibiotic, antiprotein As. Here you can see that in a similar type of mechanism, in presence of rhodium catalyst, it will generate a carbene. It will generate a carbene center here, and that get inserted into this internal double bond in a stereoselective manner and give us this cyclopropane compound. So based on that, there's one question. So draw the structure of the cyclopropane intermediate and explain the formation of the cycloheptane product in the following reaction. So here you can see there are two double bonds is there. One is this conjugated one, another is this. This is also conjugated with the adjacent double bond, but not with the OAC. This is conjugated with the OAC as well as with this double bond. Now in case of cyclopropane reaction, it usually react with the double bond which is electron rich. Now here you can see Due to plus R effect of this OSC group, there is electronic movement towards this double bond. There is electronic movement towards this double bond. Because of that, this double bond is electronically rich. This double bond is electronically rich. So, in the first step, we will generate a carbene center first. We will generate a carbene center first. After that, this carbene get inserted into this double bond. Here it will react selectively with this double bond. Here it will react selectively with this double bond. Forming this type of cyclopropane intermediate. In the next step, the cyclopropane undergoes a cleavage. This comes here. From this as our product. Okay, so in between these two double bond, which is the more electron rich? This one, because this is totally conjugated with both of them, so their electron density decreases because of this conjugation, whereas this double bond is away from this OAC group, which the minus I effect of this OAC group is less on this double bond. Because of this double bond is more reactive towards this carbene center. Okay. Let's go to the next question. So next, rhodium containing one of the important reagent is Wilkinson catalyst. Rhodium containing one of the important reagent is Wilkinson catalyst. So this type of Wilkinson catalyst undergoes a hydrogenation of the double bond. If you add this Wilkinson catalyst to an alkene, this leads to a hydrogenation, giving us alkene as our product. Giving a alkane as our product. So the rate of this hydrogenation decreases with increase of alkyl group substitution on the double bond. As much the double bond becomes bulkier, the rate of the hydrogenation decreases. There is a minimal scrambling of hydrogen deuterium in the product when the equimolar mixture of H2 is added. Means this reaction is going through a concerted pathway, so there is a very less chance of deuterium incorporation and giving us a mixture of product. So in case of Wilkinson catalyst, it always leads to a syn hydrogenation. The stereospecific syn addition of multiple double bond is followed by stereospecific reductive elimination in the hydrogenation catalyzed Wilkinson catalyst. Therefore, alkene or alkyne hydrogenation produces syn addition products using this catalyst. For instance, if the diastereoselective hydrogenation of malic or humeric acid in D2 in presence of Wilkinson catalyst has been shown. So in case of malic acid, when this Wilkinson catalyst has been performed, we get a meso compound. But in case of humeric, we get a mixture of product. Let's go to solving some problems. So from here, I have already discussed Wilkinson catalyst usually reacts with the alkene which are less sterically hindered, and there is always a syn addition. Based on that, there is some problem. So let's solve one by one. I will solve the first one for you, then I'll just give 1 minute, try the others. So here there is a compound which has a one endocyclic double bond and one is exocyclic double bond. In case of Wilkinson catalyst, the selectivity is always towards the exocyclic double bonds over a endocyclic double bond. So in this case, which double bond will get reduced? Obviously the exocyclic one, because this is less sterically hindered. Because this is less sterically hindered. Okay, let's solve the other two. I just give 1 minute. Just try once. Okay, let's solve one by one. So here, one double bond is inside the ring, one is outside the ring. But here, the double bond has 3 groups around it, there is 2. So the less hindered double bond is this one. So which one will get reduced? Obviously the external double bond. Obviously the external double bond. In this case, one is trans, another is cis. So as the reaction goes through a cis addition pathway, therefore the cis alkene will react at a faster rate compared to the trans alkene. Here 3 double bonds are there. These 2 are conjugated, whereas this is isolated. So the isolated double bond will react at a faster rate than that of the conjugated one. So this isolated double bond will react faster than that of the conjugated one. Okay. Here one is alkene, another one is alkyne. Which will react? The more electron rich is alkyne. So alkyne will react at a faster rate than that of the alkene, and it will react in a cis manner. So give us this cis alkene. Give us a cis alkene. In this case, between this benzene ring and this carbonyl and also NO2, all these are non-reactive towards this Wilkinson catalyst. So it will be selectively react with the external double bond the carbonyl NO2 and the benzene ring will be unreacted under the reaction condition. Okay, I hope it's clear. So now if whatever question comes from the Wilkinson catalyst, you will be able to solve that, because first Wilkinson catalyst will react with the less sterically hindered double bond, less conjugated double bond, in electron rich double bond, and the other functional group are unreactive towards this double bond. Exocyclic double bond will react faster rate. Okay, so let's solve some questions based on that. So the first is, what is the oxidation state of the central metal ion in Wilkinson catalyst? Which is the metal ion in Wilkinson catalyst? Obviously this rhodium. So what will be the oxidation state of this rhodium? So let's first draw the Wilkinson catalyst. Rhodium, rhodium PPH3 whole 3 Cl. There is no charge. Okay, so let's determine what is the charge of this oxidation state of this rhodium. So this PPH3 has no such oxidation state. If you consider this rhodium as a X, PPH3 has no such oxidation state, so 0, and chlorine has -1 oxidation state, and total charge is 0. So the oxidation number, total charge over the rhodium metal charge is +1. So the oxidation state of the rhodium catalyst is +1. Okay, let's go to the next question. What will be, this came in GATE previous year question. So what will be the major product P and Q for the given reaction sequence? What will be the major product in the formed reaction? So first one is, the first step they added 9-BBN followed by H2O2 NaOH, and they found P, and after that they added mesyl chloride Et3N NaOH and this Wilkinson catalyst and found product Q. So they have asked what will be the structure of P and Q. So let's go step by step. So in presence of 9-BBN, if you consider this from below the plane as represented in the answer, so 9-BBN will approach from the above the plane and in a seen manner. So this H will added here, and boron will added here. Okay, now in presence of H2O2 NaOH, what will happen? This boron, carbon-boron bond will be carbon boron bond will be replaced with a carbon oxygen bond. Carbon boron bond will be replaced by a carbon oxygen bond, giving us this as our product. So the correct option will be between A or B. Now in the next step, this OH will be acetylated. Acetylated, giving us OMS. In presence of NaOH, this OH will be hydrolyzed. O minus comes from the below the plane as the OMS is above the plane. This gets removed, and in presence of Wilkinson catalyst this double bond get reduced and we get this as our product. So the correct option is option B. Correct option is option B. Next topic we'll discuss, that is silver containing reagent. Next topic we'll discuss, that is silver containing reagent. The silver catalyzed cyclopropionation of a variety of alkenes including more hindered substrate can also be achieved. Despite that, the substrate failed to afford cyclopropion derivative with rhodium catalyst. Cyclopropionation of a variety of alkenes including more hindered substrates can also be achieved. Despite that, substrate failed to afford the cyclopropionation in presence of rhodium catalyst. So you can say I have already discussed about how rhodium catalyst can generate a carbene from this diazotype of compound through elimination of N2 gas. This type of carbene can be inserted into this double bond and generate cyclopropan ring. This type of substrates sometimes are not that fail to form the cyclopropan from this type of alkene, but in presence of silver catalyst we can get our desired product. In this case also, in presence of silver catalyst we get higher yield of this type of product. Silver catalyst reagent can be, silver catalyst can also be used for homocoupling of alkyl Grignard reagent. Here if we add this dibromine compound to this Grignard catalyst, we can generate the homocoupling of this Grignard catalyst. The mechanism is like this, where this Grignard undergoes a transmetallation type of reaction with this silver catalyst. Then through addition to this alkyl bromide, it generates this alkene, and when two silver alkyl species combine, it get our this homocoupled product. This also has been used for cycloaddition reaction. The thermal reaction between methyl propionate and aridine imine was slow in absence of silver acetate, but in presence of silver acetate, the rate of this coupling reaction increases. Here the reaction goes through this type of intermediate. Silver catalyst, one of the important reaction is Prevost reaction. Prevost reaction is a chemical reaction in which an alkene is converted by iodine and silver salt or benzoic acid to vicinal diol with anti-stereoselectivity. So in this case, in Prevost reaction, from an alkene we get a diol compound, and in case of this reaction we selectively get an anti-diol as our product. If you see the mechanism, here you can see the first, this acetate, the iodine will coordinate with this double bond, form this iodine compound, iodinium type of species. Then this acetate anion will attack one of the center and it will open up. After that, this undergoes a intramolecular substitution reaction and form this type of species. Now in in medium the benzoate ion is still there. It will attack here. It will open up and get this type of trans product. Now after that, if you perform hydrolysis, we can get with this both the ester will be hydrolyzed and we get this type of anti-diol. There is a similar type of reaction called Wood-Wyatt hydroxylation. In this case, just comparatively, we just get the cis-diol. In case of previous, we get a trans-diol, but in case of Wood-Wyatt, we get a cis-diol. The difference is in medium, if we use water, all the reagents are same. But if we use water in the medium, we will get a cis-diol. Here you can see in this reaction, no water has been used. The first step, no water has been used, so we are getting this acetate. After this first step, we are using water. But here, if in the first step, along with this acetate, you use water, then in that case, we will get a cis-diol. We get a cis-diol. So mechanism is quite similar. Up to this, mechanism is quite similar. In this case, instead of this benzoate anion, the OH will attack to this carbonate species and it will open up and form this type of monohydroxylated compound. After that, if you perform the hydroxylation of this one, it will hydrolyze another and we will get a cis-diol. Now this bicyclic ring has been given and they have added silver acetate, iodine and H2O. H2O has been given along with the first one. So the reaction will be Wood-Wyatt. This is a Wood-Wyatt reaction, not Prevost. Prevost is a dry condition. Prevost is a dry condition reaction. No water is added in the first step. In case of Prevost, this type of acetate is being isolated. After that we perform the hydrolysis. But in case of Wood-Wyatt, we won't get that this diacetate compound. We can isolate this compound and after hydrolysis we get this dihydroxylated compound. So in this case, this CH3 is above the plane, so the above plane is already occupied. So iodine will approach from the below the plane. Iodine will approach from the below plane. So that in the next step, OAC will attack from the above the plane because the iodine is already attached at the below the plane. So it will approach from the above the plane and it will open up. In the next step, this, as I have shown in the mechanism, this acetate will attack again to this center and remove the iodine from the system, from this cyclic species. after that, as in medium water is added, so both this carbonate, both this hydroxy will be hydroxylated, hydrolyzed, and give this cis-diol. So this is a Woodward reaction, so it will give a cis-diol. Both the carbonate will be hydrolyzed and we will get a cis-diol. Okay, I hope it's clear. What will happen in this case? Now you can see this double bond is, both these double bond are conjugated with this carbonyl compound. This is alpha beta unsaturated compound. This is also conjugated with the extended conjugation. So due to conjugation, this iodine will not able to coordinate with this double bond, whereas this double bond is isolated, so this is more electron rich. So iodine will coordinate with this double bond, and as CH3 is above the plane, so iodine will approach from the below the plane. Now in this reaction, along with the first iodine and silver acetate, they have added water. So this is a Woodward reaction. This is a, from the reagent you will get idea, whenever the water is added in the first step, that is called Woodward reaction, and if it is a dry reaction, that is called reversed. What Woodward means? Cis-diol. So as the CH3 is above the plane, so iodine will approach from the below the plane. Again the acetate will approach from the above the plane, like the first problem. So the dihydroxylation will be like this. Rest part will be similar. I am just drawing this part. So the dihydroxylation will be like this. Okay. I am not drawing the reaction mechanism. If you have any doubt, you can ask me in the next class. I hope it's easy. What will happen in this case? I just give 1 minute. Try. So in this case, from the reagent you can see there is no water is added. There is no water is given. So this is a pre-host reaction. This is a pre-host reaction. Pre-host means anti. Okay. So let's go step by step. Here all the double bonds are conjugated. Only this one is isolated. So which will react? This one. This double. So I am just keeping others. Just all other part will be this. I am just showing this part. So iodine will conjugate it. After that, the next step, this OCOPH will attack from the below the plate. Will attack from, as it is above the plate, so it will attack from the below the plate, and this rig will open up till this acetate and remove the iodine from the system. After that, in the next step, so this cyclic intermediate will be formed. The next step, as the acetate is already remaining in the medium and no water is given, so this will enter, will form a trans benzoate product. Other part will be same as in the substrate, so I am not drawing that. The remaining part will be same as shown in the substrate. Okay, it's clear. Let's go to the next question. So based on the silver catalyst, there are some other silver can be used as a Lewis acid, which can coordinate with this halogen and promotes the substitution type of reaction. So let's go step by step. In this case, in the first step, here role of silver is just acting as a Lewis acid. There is no such alternative factor. The factor is mainly controlled by the substrate. So here bromine has a anti-AH with respect to this bromine atom, but there is no such H. This H is not anti to this bromine atom, but this bond is in anti-periplanar with this bromine one. Okay, so let's go to the first one first. What happened in this case? As this H is already anti with this bromine, so in presence of silver, it will just bromine will coordinate with silver and undergoes the elimination. So H will comes here, so it undergoes a E2 elimination. This undergoes a E2 elimination and form this as our product. This is a enol form, as it is in the enol form, it undergoes a ketone type of tautomerism. So it goes here, comes here. So the correct product will be the cyclohexane where this methyl is above the plane. Okay, but in this next one, there is no such H which is anti-planar with this bromine, because this bromine is above the plane and H is also above the plane. So both are in the cis manner, both are in a cis way. So there is no such possibility of elimination reaction. But if this bond, this carbon-carbon bond is in anti-planar with this H atom, a bromine atom. This CC bond is in anti-planar arrangement with this CBr bond. Because of that, this OH will comes here and this carbon-carbon bond breaks and shifts to this carbon center and eliminates this bromine from the system. So this, because of unavailability of anti-peripheral H, this undergoes a ring cleavage. So the correct option will be option C. So the correct option will be option C. Understood? Whenever there is an anti-peripheral H is available with the living group, it will undergo a simple elimination reaction. But if there is no such anti-peripheral H is available, but there is a carbon-carbon bond is there which can undergo the, which can has the arrangement of anti-peripheral arrangement with this living group, it can undergo the elimination like this way. The correct statement with respect to the stereochemistry of alpha hydroxy acids P and Q formed in the following reaction. Here there is no such silver catalyst is added, but here silver catalyst is added. In this case, as no such, it will undergo the simple substitution type of reaction, so it will come here and eliminates. So it will be, here the bromine is above the plane, so the OH will come from the below the plane, so there will be an inversion of configuration. There will be an inversion of configuration. But in this case, whenever silver catalyst is added and H2O is added, the reaction is going through a H2, the hydrolysis pathway. Whenever H2O is added, that means the nucleophile is mild. The nucleophile is mild. So reaction gets some time. The reaction is not that faster than that compared to SN2 type. This go through a SN2 type of mechanism. But in this case, as the nucleophile is water, which is a mild nucleophile, the reaction goes through a SN1 pathway. Reaction goes through a SN1 pathway. Because of that, this bromine will coordinate with this bromine will coordinate with this silver catalyst and get removed from the system and generating this carbocation species. After that, this OH will attack from the same plane, leading to a retention of configuration. The correct option is option D. P will be inversion of configuration, whereas Q will be a retention of configuration. The correct statement about the following transformation. So they have given this substrate. So this is not substitution or non-elimination. So silver catalyst can be used in case of cycloaddition type of reaction. So in this case it undergoes a ring cleavage. So in presence of heat, now between this bromine and chlorine, which will be eliminated? As we know, carbon-bromine bond is weaker than carbon-chlorine bond. So it gets eliminated at a faster rate than that of the chlorine. Carbon-bromine bond is weaker. So this comes here. And bromine get eliminated from the system. So the correct option will be product B. Correct product will be product B. Now the ring opening will be coordinatory or desetatory. So this reaction is going through only one bond is getting involved. Only one ring bond is getting involved. So the reaction is going through a 2-pi system, that is 4n plus 2. 4n plus 2 in heat undergoing a desulatory system. So the correct option is option D. Oren plus 2 and heat, so it will go through a this type of mechanism. So correct option is option 4. Okay. So is one of the question. It is kind of miscellaneous. I have discussed about this topic earlier also. Just for a recap, I am discussing this one. So what will be the correct? There is another question came in June 2012 based on the silver catalyst. A reagent A required and the major product B formed in the following reaction sequence. So they have asked for the reagent A required to get this fused 5-3-member ring fused, and after that they added AgNO3 and H2O and did ask for the product form. So let's go step by step. So from the reaction, from the product, you can see there is a formation of cyclopropane from this alkene. So obviously this reaction is going through a carbene pathway because there is a cyclopropanation reaction and it occurs through a carbene. Now there is, the carbene should have 2 bromine atoms. So the carbene should be like this. The carbene structure should be like this. This type of carbene can be generated from chloroform, tribromomethane and any base. So this reaction in this pathway, it can generate this carbene species. This reaction takes place through a alpha elimination. If you know about this alpha elimination, there is an extra class in the last. There I will try to discuss about all these extra topics which are not included in this chapter, but somewhere included, like this elimination, substitution. I will try to give an overview of that. So through alpha elimination, in presence of base, this H minus is eliminated and there is a generation of negative charge and 3 bromine are there. So this bromine leaves the system with this negative charge and generate this carbene. Okay. So the correct option will be between C or D. So A and B are already cut. So the correct option will be between C or D. Now the next is what will happen if you add AgNO3. As we said, AgNO3 acts as a Lewis acid and promotes the substitution reaction. So if both the bromine are in same nature, see if it coordinates one of the bromine and this leaves from the system. So to remove generating this type of carbocation, now this type of carbocation are highly unstable. To stabilize this one, the bond breaks and form this type of 6-member ring with a positive charge here and a double bond here. So this becomes 2 degree unstable, whereas this become get some stability due to conjugation. So this is stable. Now, as water is in, so I missed one bromine atom here. So water attacks at this positively charged center, and the correct option is option C. Correct option is option C. Okay. Let's go to the next question, which is also based on the silver catalyst. So the major product formed in the following reaction. They have give this diazo type of compound and silver oxide in presence of lime. So this type of reactions goes through a special type of intermediate. So first, in presence of silver catalyst, we know there will be a elimination of N2 gas and generate a carbene center. This we have already discussed. Carbene center. Now this carbene center undergoes a rearrangement type of generating a ketene moiety, In this case, while this rearrangement, this chiral center is unaltered during this course of the reaction. Because of that, the stereochemistry of this chiral center will be intact. Stereochemistry of the chiral center will be intact. Now, as in medium, methanol is there. So methanol will attack to this ketene center. Giving this as our product. So the correct option is option A. Correct option is option A. Okay. So it was so this reaction goes through a special type of intermediate. This is called ketene intermediate. Ketene. It's also known as a Smith reaction. It's also known as a Smith reaction. Okay. So this much for today's class. I hope you enjoyed. So I'll just give an overview of the class. So today we discuss about transition metal containing catalyst, mainly rhodium and silver catalyst. So rhodium catalyst can be used for Wilkinson catalyst as a Wilkinson catalyst for hydrogenation reaction, and their selectivity I have shown through different type of examples. Then we move to different questions, previous year questions based on this Wilkinson catalyst. Then we solve some applications of silver catalyst. This can also be used for carbene generation and also cycloaddition reactions. Then one of the important silver containing reagent is Prevost reaction and Woodward reaction. I have discussed about the mechanisms. Then we solve some questions based on that. and then other some question based on the silver catalyst, where the silver catalyst can be act as a Lewis acid, followed by this one. So this much for today. Thank you everyone.